So,
okay. Ming can go ahead and introduce Tanmay.
Okay. Today we are very happy to have Tanmay giving a talk here. He is now in India, so it's quite early for him there, and he graduated in Shanghai, right? In 2016, and now he's in India. Today he's going to give a talk in implementation of quantum measurements using classical resources and only a single ancillary qubit. And maybe Tanmay can also introduce yourself again, and then everybody can know better. Okay,
Sure.
please go ahead. Thanks. Let's welcome you.
Yeah, thanks. So yeah, I'm Tanmay Singal, and I completed my PhD in 2016 from the Institute of Mathematical Sciences in Chennai. From there, my topic of my work over there was quantum state discrimination. I went on to Korea in Hanyang University, Korea, in Professor Junwoo Bae's group to continue quantum state discrimination, and thereafter I started pursuing error correction as well. And then afterwards, I went to Shanghai and Fudan University. I wanted to do error correction, but because of the pandemic circumstances, I had to resign, and I joined. I was remotely working in the Center for Theoretical Physics in Polish Academy of Sciences with Michal Uzmania's group. And so this work came about over there. So I was not able to join the Center for his group physically, again, because of the pandemic. And right now I'm remotely affiliated with Milan Musoni's group in Budapest University of Technology and Economics. Sorry, it's Budapest University of Technology in Mathematics and Economics. So there's something wrong here. Right. So this work is about quantum measurements and the implementation cost of quantum measurements. The title is Implementation of Quantum Measurements Using Classical Resources and Only a Single Ancillary Qubit. It's been, I did this with Filip Marchevsky and Michal Uzmaniak while I was in Fudan as well as in Center for Theoretical Physics. And this was recently put on the archive. So the archive number is over here. So let's get started. Right. So I'll first give an outline of this presentation. Okay, so first I'll talk about the problem, that is the cost of implementing a general quantum measurement. Okay, now to implement a general quantum measurement, some resources are required. So we partition these resources into two categories: classical resources and quantum resources. Then a scheme to implement the most general quantum measurement using only a single ancillary qubit with post-selection will be presented. Okay. Having presented this scheme, okay, what we will do is we will try to analyze whether this scheme is good or bad. And then we will use analytic results and numerical results to motivate the fact that the scheme performs pretty well. Based on the performance of this, on this evidence, we formulate a conjecture, and then we go to the analysis of noisy implementation. That is, if the circuits which are implementing this most general measurement using this scheme are noisy, how well does it perform? And then afterwards we conclude. So this is the outline of the talk. So I'll just begin with what are measurements in quantum mechanics. Well, when you have a quantum system and you want to extract some information out of the system, you have to perform a measurement on it. Okay, this is a probabilistic event, and the probabilities of various outcomes are given by Born's rule. Okay. So the most general quantum measurements find applications in many different scenarios in quantum information theory and quantum computing. Quantum communication, quantum state discrimination within quantum communication is one example. There is metrology, tomography, and in quantum computation, the hidden subgroup problem specifically uses like the most general quantum measurements. Okay. Now, what do I mean by most general quantum measurements? What do I mean by simpler measurements? Well, let's first talk about simpler measurements. What happens in a simpler measurement, that is a projective measurement, is you have some quantum state, you perform some measurement of some observable upon it, you get some outcome, and that's it. That's your measurement. So mathematically, how is this measurement described? Well, it is described by a set of positive semi-definite linear operators, Pi, which sum to the identity, and they are such that they satisfy this orthogonality relation. Actually, this should be pi pj times pi. There should be a pi over here as well. So these are projective operators. In contrast, what are most general quantum measurements? Well, in this case, you have some quantum state, okay? You attach to it a fixed ancillary qubit, sorry, a fixed ancillary system, okay? And then you perform a projective measurement on this combined system and get outcomes. This gives you a most general quantum measurement, also known as a positive operator valued measure. And this description of realizing this most general quantum measurement, that is attaching a fixed ancillary system and then performing a projective measurement on the entire thing, that is known as Nymark's dilation theorem. Okay. Mathematically, how is this described? Well, it is described by a set of positive semi-definite linear operators Mi. Okay, there are a little n number of them with sum to the identity. Okay, note the fact that this orthogonality relation is not present over here. Okay, so these are more general. So this is the most general quantum measurement. Now, the most general quantum measurement implementation requires that if suppose your principal system, okay, is that of n qubits, then what is the size of the ancillary system that you need to attach to this to implement the most general quantum measurement? The size is also of n qubits. Okay, so n qubits your principal system and n ancillary qubits. You perform a projective measurement of that. That gives you the most generalized quantum measurement. Okay, so this is something that was done in 2017 by Mihail Usmaniak and his collaborators. Now, as n increases, as the size of your principal system increases, you can imagine that the implementation of this generalized Nymark dilation theorem becomes quite problematic. Why? Because you require more ancillary qubits, which implies that your circuit width will be larger, and this will lead to a more noisy implementation of this generalized Nymark dilation theorem implementation of this measurement. And then, like, from the perspective of near-term quantum computing, you have other issues like limitations of qubit connectivity, etc., etc. So what is it that we would like to do? Our motivation in this entire work is to find ways of implementing the same measurement, but with fewer ancillary qubits. Okay, so you have an n qubit system over here, and the most general Nymark dilation theorem requires you to attach n ancillary qubits. We would like to see if there is some way in which you can reduce this number of qubits, ancillary qubits. Okay, so that is the problem, and I told you what we want to do, what our motivation is. Now let's come to what are the resources that we can implement, okay, that we can sort of use. Okay, we assume that classical randomness is free. Okay, so then this frees up two of the following operations. One is known as classical mixing of POVMs. Okay, so what happens over here is that you have some state and you have the ability to implement one of two measurements at a time. Either implement the measurement M or implement the measurement K. So what you do is you implement the measurement M some certain number of times, and you implement the measurement K the remaining number of times. On average, what happens is that you end up implementing another measurement, that is L, which is a probabilistic mixture of the first measurement and the second measurement with the frequency probabilities. Okay, so that is one of the free operations you can do. This is known as classical mixing. Next is classical post-processing. What happens over here is that you have the ability to implement some measurement M. Now, this measurement has certain outcomes, M1, M2, so on and so forth. Once you perform this measurement a certain number of times, and then you perform a certain kind of coarse graining of these measurement outcomes. That is, you recombine the measurement outcomes in various ways. Okay, you can either increase the number of outcomes or decrease them, you can mix them or whatever. Okay, this is known as classical post-processing. Okay, and on average, you end up implementing another POVM, which is written as calligraphic Q of this same M, which you originally implemented. Okay, so our free operations are classical mixing of POVMs, that is of measurements, and classical post-processing of measurements. These are our two free operations that we can use. Okay, now there is another operation that we can use. Okay, but this is not going to be free. Okay, now for that I have to first introduce another notion, that is post-selection. Okay, now what is post-selection? Well, you have some measurement L. Okay, the outcomes of this measurement are divided into two categories. Okay, you have like I1, I2, so on and so forth, and you have J1, J2, so on and so forth. Okay, so the I's outcomes, these are outcomes that you are interested in. Okay, and the J outcomes are outcomes that you don't care about. Okay, so what you do is you perform this measurement L. Okay, you sample only from those outcomes which you consider are useful, and then you reject or you discard of all those outcomes which are useless. Okay, this is known as post selection. Okay, this is not necessarily going to implement a measurement. Okay, this is just simple post selection. But in certain circumstances you can end up implementing a certain measurement L by performing another measurement L and then performing post selection. When is that the case? Well, suppose this measurement M which you want to simulate and the other measurement L which you can implement, suppose they are related by this equation. What is going on in this equation? Well, L is the measurement that you can implement. Okay, M is the measurement that you want to implement, and suppose the outcomes of M are the outcomes of when are M are in, let's say, the first few bins of the measurement L, and the remaining outcomes of L are some other outcomes which you don't care about. So when you have this scenario going on, then what you do is you can post select on those outcomes of L which correspond to M, okay, and you discard of all the remaining outcomes. Okay, now this ends up implementing this POVM M with a success probability which is given by Q success, and that is the same coefficient that you see over here. Okay, so this is how you can implement a POVM M, sorry, simulate a POVM M by actually performing L and then using post selection. Okay, so these are our three operations. So as noted, this operation is not free. But why is it not free? It's not free because there is a cost. Okay, you have to discard of all the outcomes which correspond to this this POVM. Okay, so that is the cost of and you end up implementing your target POVM M with a certain success probability. Okay, so this is the cost associated with the implement for this scheme of implementing M. Okay. Right, so now let's come to the scheme. So what scheme are we proposing? Well, let M, okay, be our target POVM. We want to implement this, okay, and we want to implement this using only one single ancillary qubit, okay. So over here you have the outcomes. So the POVM, okay, so these M1, M2, they are known as the POVM effects. I did not mention that in the second slide, but yeah, these are known as the POVM effects, okay. And let's just assume for simplicity that the rank, okay, the operator rank of these POVM effects, that is equal to 1, just for simplicity. Okay. So the number of outcomes over here is little n. What does the scheme demand? Well, the scheme demands that you choose a partition of this number, of the set 1, 2, 3 up to n. Okay, so this symbol over here, this symbol stands for the set of numbers 1, 2, 3 up to little n. Okay, now you choose some partitioning of this set. Okay, so x1, x2, so on and so forth. Okay, such that the size of xi, okay, for all the i's over here, that is equal to some little m. Okay, here, so okay, yeah, so over here you have k partitions and k is equal to n by m. Now you may say that it may be the case that you cannot necessarily find some integers k, n, and m such that they will be related in this fashion. Well, in that case, you choose the first k minus 1 elements of your partition to be of size m, and the kth partition you can choose it to be of whatever remaining size. So this equation won't be satisfied in that case, but this doesn't matter. Like, the scheme holds even more generally, but this is chosen over here just for simplicity, okay, of presentation. Right. So now, corresponding to each of these subsets of n of this this set, okay, you associate a corresponding POVM. So with x1 you associate with a measurement nx1, to x2 with x2 you associate a measurement nx2, so on and so forth. Okay. Now, these nxi's, there is something special about them. What is special about them? Well, they are such that each of them can be implemented using a single ancillary qubit only. Okay. Now you may say that, okay, great, but like, how do you construct them? Like, what are how are these guys related to your original target POM? Well, I'll come to that on the next slide. For now, let's just imagine that we have these POVMs. Okay, right. So how do you implement? So what is the scheme? So this figure gives you the scheme. Actually, the left hand side of this figure gives you the scheme. So what you do is you have your state row. You perform these POVMs nx1, nx2, so on and so forth with some a priori probabilities. You implement these guys. Okay, with some fixed probabilities. Once you obtain the outcomes, you perform some classical post-processing on these outcomes. And after the classical post-processing, you perform a post-selection. Okay, so you use all the three operations, that is classical mixing, which is a free operation, classical post-processing over here, which is also a free operation, and finally you have post-selection. Remember that this is not a free operation, it has a cost. Okay, so all of this is done. I'm not giving you the details of like what exactly is going on, how do you perform classical mixing, post-processing, etc. I'm not giving you all that detail, but I just want you to, yeah, so basically just to give you a picture, what's actually going on cumulatively is that you end up implementing this scenario over here. So you end up implementing the target POVM M with a success probability Q success, and with the remaining probability you get some junk outcomes which you're not interested in. So this is your entire scheme. Now let's come back to the original question. What are these measurements nx1, and how do you construct them from these subsets x1, x2, so on and so forth of this set? Okay, so again over here you have your target POVM. Now let's do one thing. For the sake of simplicity of explaining this scheme, let's choose a partitioning. So remember that you had a partitioning, okay, of the set of numbers 1, 2, 3 up to n, okay, and x1, x2, they are subsets such that all of them are disjoint and they cover n. Okay, for simplicity, let's just choose x1 to be the numbers 1 to little m, x2 to be the numbers m plus 1 to 2m, and so on and so forth. Okay, let's just choose this simple partition. So what you do, how do you construct these nxi's? Well, nx1 is constructed using the POVM effects of the first m POVM effects that appear in this target POVM. Okay, so you take m1, m2, so on and so forth from here, and you put that into nx1. m plus 1, m plus 2, so on and so forth, up to 2m, you put that in nx2, so on and so forth. Okay, of course, you will have to add another remaining POVM element so that nx1, all these effects by themselves will not sum to the identity. Okay, so what you need to do is you need to add another POVM element, another effect to this set. Okay, so that will give you m plus 1 outcomes over here. Similarly, you'll get m plus 1 outcomes over here, so on and so forth. Okay, now the constraint. So I also mentioned the fact that each of these POVM effects, they have to be such that they can be implemented using only a single ancillary qubit. Now, where have I put that information inside? Where have I put that? Where have I included that like in that requirement in this construction? Well, this m has to be such. This little m has to be such that it is less than equal to little d. Oh, I forgot to mention. Sorry. So little d is the dimension of your principal system. Okay. So when m is less than d, and given the fact that the rank of this mi they are equal to 1, all of that will ensure that each of these nx1, nx2, so on and so forth, these are implementable using only a single ancillary qubit. Okay, so this is how you construct these nxi's, right? And the success probability, the success probability actually has a simple form in terms of these POVM effects. So what you have over here is you have two summations where the inner summation sums over all the POVM effects that occur within a subset of the partition. Then you take the operator norm, that is the largest eigenvalue of that. And okay, yeah, so largest eigenvalue, because MIs are all positive semi-definite. So, I mean, they're Hermitian, so sums are also Hermitian, and hence you can take the largest eigenvalue of that. And then you sum all those largest eigenvalues for each of the partitions. And then you take the reciprocal of that thing. That gives you your success probability. Okay, so this success probability has this form from these POVM effects. Okay. Now let's discuss a little bit more about our success probability. Note the fact that the success probability actually depends on your choice of partition. Okay, so you have some partition over here that you've chosen, and the success probability, it depends on this choice of this partitioning. So when you have different partitioning choices, then you will get different values of Q success corresponding to the choice of partition that you have made. Now, to maximize the success probability requires that you optimize, that is maximize over all possible partitions. Okay. Now, firstly, what is the physical interpretation of this Q success? Well, Q success tells you that if you want to sample once from your target POVM, you need to implement this scheme 1 by Q number of times on average. Okay. So the lower the value Q success, the larger the number of times you have to implement this scheme so that you can sample once from it. Okay, so that is undesirable. Hence, it is good that Q success is as high as possible. That's why I was talking about maximization of Q success. Okay, so Q success is the figure of merit of this scheme. Okay, and Q success actually can also be related to other resource theoretic quantities of interest. Okay, we will see this in some time. Right. So I've presented the scheme and we've looked at it. Now, is the scheme good? Is the scheme bad? What about that? Okay, let's have a discussion on that. Well, to do that, let's compare this scheme with an earlier scheme, which is similar. Okay, so this earlier scheme was, it came out in 2019. The authors were, again, my collaborators, Michal Osmania, Filip Maciejewski, and a third person whose name I find a bit difficult to pronounce, Zbigniew Puchawa, I think. I'm not sure. So what happens in that scheme? So in that scheme, you simulate an arbitrary POVM with only classical resources and no ancillary qubits. So remember, in our case, what we're opting for, simulating an arbitrary measurement with classical resources and a single ancillary qubit. But in this case, they tried no ancillary qubits. Okay. And what do they find there? They find that in the worst case, okay, this Q success goes over 1 by D, where D is the dimension. Now you can imagine that as the dimension starts increasing, okay, the Q success starts decreasing. Particularly note the fact that D is exponential in the number of qubits. Okay, so Q success as a function of the number of qubits would be of the would be E minus n, e power minus n. So that is not at all desirable, right? What happens in our scheme? Well, the scaling of Q success we find to be significantly better, and we expect that it is actually above a constant for all measurements in all dimensions. Okay, this is what we expect. And we have strong evidence for this statement, okay, that the Q success is above a constant for all measurement in all dimensions. We have evidence for that in the form of analytic results and numerical results. Okay, so what I will do is I'll first go to the analytic results. Now, to explain analytic results, I first need to explain what hard random POVMs are. What happens in hard random POVMs? So this schematic depicts the way of implementing these hard random POVMs using this Nymark's dilation theorem. Okay, so you have your state rho, you fix it with, you attach to it some fixed ancillary system, and then you perform a rotation on this combined system. This rotation actually is a hard random rotation. Okay, and then finally you perform some fixed POV, some fixed projective measurement on this combined system. Okay, so this scheme ends up implementing a hard random POVM. Okay, so what is it that we, so for hard random POVMs, how does this scheme work? That is what we would like to know. Okay, so I'll present a simpler version of this result, okay, where the number of outcomes is D square, D is a dimension, and your little m, that is equal to D. Okay, so what you do is you fix some partition. Okay, I'm not optimizing over partition, I'm fixing a partition from the outset. Okay, so x1 is 1 to like up 1 to up to D, x2 is D plus 1 up to 2D, so on and so forth. Okay, so these partitions are fixed, and with respect to this partition, the Q success then becomes a function of the unitary. Okay, so now what you do is you equip this unitary with this hard probability measure. Okay, what is that? What happens then is this Q success becomes a random variable on your unitary group. Okay, so what is our result? Our result basically is this inequality. Okay, but before I explain this inequality, I just want to mention the fact that we also have results for general value of n. Okay, that is the number of outcomes of your target POVM, and m. Okay, where m is the number of n plus 1 is equal to the number of outcomes of the smaller measurements nx1, nx2, so on and so forth, which you can implement with a single answer with a single ancillary qubit. Okay, so yeah, now let's come to the result. So the main result is given over here. Okay, so what is going on over here? You have an inequality. Okay, where on the left hand side you have some probability, and on the right hand side you have some upper bound to that probability. Okay, so to explain this, let's use a diagram. So for each unitary, okay, you can implement, for each unitary, you get a corresponding POVM, and then for that you get a corresponding probability of success for your for that choice of partition. Okay. So what is the problem? So because you have invoked the Haar measure on the set of all unitaries, this Q success becomes a random variable on your unitary group. Okay. So what you want to do is you want to study how this, like what are the properties of this random variable. Okay. Particularly, you want to know its concentration. So this inequality studies its concentration. What it says is that, so suppose you consider the set of all those unitaries for which the Q success is greater than 6.5%. Okay, so that is given by the green set over here. And then Q success being less than 6.5%, the set of unitaries is given by this red set over here. Okay, so that is this one. So
oh, sorry. May I ask a question?
Sure.
Okay, can you define again what Q success means here?
Q success is the probability of being able to implement your target POVM for this particular value of U. What do I mean by that? Okay, let's go back to this diagram. Okay, so this diagram gives you, so okay, so over here, like I've said that U is hard random. Okay, so forget about the hard random part. Let's assume that U is some POVM, U is some unitary. Okay, so it's a unitary on the joint system of your original like state and like, you know, the ancillary qubits. Okay, so right, so so your original system is d-dimensional and you have to attach a d-dimensional ancillary, so you get totally a d square dimensional system, and then U is some unitary on this d square dimensional system. Okay, so you perform some projective measurement, you fix a projective measurement. This gives you a POVM, right? So this is the POVM that you want to implement. Okay, but in this, so what you do over here, what you're measuring, this Q success over here is the probability of implementing the same POVM for this U, but with the other scheme which I presented earlier on. That is what Q success is.
Yeah, so that means from at the measurement part, you will get d squared possible outcomes. Is that right? So from
I mean, yeah, your target POVM has d squared outcomes, yes.
Okay, and from those d squared, we want to know if we can deduce. Yeah, I see. Okay, thank you.
Right. So, like just to sort of give a bit more explanation. So look, if you implement Naimark's dilation theorem, I mean, if you implement this scheme, okay, then you have only d square outcomes. Okay, fine. But when you use the scheme that I like introduced earlier, a little bit earlier in the talk, then you will have d square plus 1 number of outcomes. Okay, where the initial d square outcomes are sort of the desirable outcomes and they sample from your target POVM. The final outcome, that is the d square plus 1th outcome, that is like say a junk outcome. You don't care about that. The success probability of that outcome will be 1 minus Q success, and the success probability of the cumulative of all the earlier outcomes, that is this Q success. Okay, so that is basically just to give you an idea of what is sort of going on when you implement it using our proposed scheme. Right, so I'll continue unless you have any further questions.
Yeah, well, good.
Right, so now let's start scaling with D. Okay, so what's going on over here? Well, it says that the probability of this red guy, remember the red guy is where Q success is less than 6.5%. The probability of this red set, the volume of this this subset with respect to the Haar measure, actually you can, yeah, the probability actually of this subset that decreases with this scaling. So you can imagine that as D increases significantly, the probability that you will simulate your target POVM with percentage 6.5% is extremely high. Sorry, with larger than 6.5% is extremely high. Okay, right. So now you may say, okay, fine, that is great, but over here you're implementing hard random POVMs. This is not a statement on any POVM, right? Well, that is correct. The point is that you see your most general POVM, any POVM, okay, which is rank 1, that is very likely to be situated somewhere in this green set, okay. And when you implement it in the laboratory, then you're not implementing precisely that point sitting in this UD square. You'll be implementing, let's say, some some open ball like around that point, okay. And you can be assured that that open ball will, as if D is large enough, that open ball will be somewhere within this, entirely within this green guy, okay. That is basically what assurance this this result tells you, and it is in that sense that this is a fairly strong result, okay. Right, now that was the analytic result. Now let's come to the numerical result, okay. So what was done in the numerical result is that you choose some set of POVMs, okay. So, and you then implement these POVMs you simulate the implementation of these POVMs using this scheme that we propose, that is a partitioning and post-selection method. And then you want to see how does the success probability for this family of POVMs, how does it vary as the dimension. So this is the plot that we get. So on the y-axis, we have the success probability, and on the x-axis, we have the dimension of the subsystem. So the two families of POVMs are SIC POVMs, okay, symmetric informationally complete POVMs, and random POVMs, okay. And over here you have this line of 25%. You can see that as the dimension is very low, the success probability is extremely high, but it gradually reduces, but then it starts plateauing almost to become a straight line at this 25% mark, okay. So this is the case for SIC POVMs and random POVMs as well, okay. And then we also did it for another family of POVMs which are informationally complete, but they are non-symmetric, okay. In this case, we again plot the success probability on the y-axis and the dimension on the x-axis. You find that there is a decrease and there is a plateauing here, but this plateauing does not necessarily lead to like a straight line. So when you plot the logarithm of the success probability, you don't get an indication that this becomes a straight line. So, and the success probability over here that we find for some of these outcomes is around 19%. So earlier it was for 25% for SIC POVMs and random POVMs, but for IC POVMs we get 19%, which is lower, but it's still a significant amount of success probability. It tells you that approximately you have to, if you want to implement any of these POVMs, approximately you'll have to implement this scheme 5 times so that you can sample once from your scheme, right? So based on these results, we conjecture the following. For any POVM, the success probability of simulating this POVM using our method is some constant C, and this constant is independent of all dimensions, okay. So this is what we conjecture. Now if these so what are the consequences if this conjecture is true? Well, it tells you that you can implement this scheme for fairly high dimensions, and the scheme is feasible. And there are some consequences from resource theoretic standpoint. I'm not very familiar with this. So for quantum state discrimination, basically it tells you that you do not have to use too many ancillary qubits to perform a decent quantum, to discriminate among the set of states in your ensemble well. Okay, so that is one thing. And then second is it also has consequences on the robustness of randomness extraction. I'm not very familiar with this. So yeah, I think basically Mihal has some ideas about this. Right, so now finally I'll come to the last part of our work. So what is happening over here is that, look, we have two schemes to implement some target measurement, right? One is your earlier NIMARC method, okay? And the other is our method that we talk about, right? That we present over here. So let's do one thing. Let's see that, suppose your implementation, the circuits that you implement these measurements with, okay, they are noisy, okay, and let the noise model be this depolarizing noise, where this eta is the, it's called the visibility factor, and it depends on the gate complexity of your circuit. Oh yeah, I forgot to mention the target POVM that we chose over here is a hard random. It's basically a random measurement, okay. with d-square outcomes. Okay, so this is our noise model. Okay, and eta, this visibility factor, this depends on the gate complexity of your circuit. Right, now let's first talk about the standard NIMARC method. Now remember, in the standard NIMARC method, your original system that you want to implement the measurement on, that is, you want to implement the hard measurement on this system of n qubits. But to implement this, this POVM, you need to attach n additional ancillary qubits as well. So the total number of qubits is 2n. Okay, and the gate complexity for a hard random circuit on 2n qubits, that has a scaling of 2 power 4n. Okay, so what you find is that this visibility factor, this decreases as this power law. Okay, so this is for the standard NIMARC method. What happens in our scheme? Where in our scheme, to implement the same hard random POVM on these same original n qubits, you need to attach only one additional ancillary qubit. Okay, the gate complexity for this is 2 power 2n, and because the gate complexity is lower, you find that the visibility factor is also it's higher. So while you still get like this power like behavior, you feel that our scheme performs better, significantly better. Okay, and I must also mention that this is the same noise model that was employed in Google's demonstration of quantum advantage in 2019. So yeah, this is the noise analysis part. Right, so now I will just summarize like the contents of this talk. So we saw that to implement the most general POVM on n qubits, you require to attach n additional ancillary qubits. Now, as n increases, this has implementation issues, especially from the near-term quantum computing, that is NISQ perspective, of noisiness and limitations of qubit connectivity, etc., etc. So to overcome this, we propose a scheme to implement the most general POVM. This requires only using classical resources and one single additional ancillary qubit. Okay, so you have n qubits originally, and you need only one more additional ancillary qubit. And the cost of implementation, we found that the cost of implementation is this Q success, and there is strong evidence that Q success is above a constant for all measurements. Okay, we have analytic results which tell us that Q success is greater than 6.5% for an overwhelming probability of POVMs. And then from numerics, we have for SIC POVMs and random POVMs, we have that Q success is 25%. For IC informationally complete but non-symmetric POVMs, we have that Q success is around 19%. Based on this, we conjecture that Q success is above constant for all measurements in all dimensions. And finally, we study the noise compounding in circuits which implement our scheme versus NIMARC dilation method. Okay, and we find that our scheme performs better there. So this is the summary of the work. Finally, let's come to the scope of our results. Well, scope and experiment is that you only need to use one single ancillary qubit, and Q success is fairly high, okay, for arbitrary dimension. Okay, so you don't have, as Q success, as dimension increases, you don't have to worry about this Q success. Okay, now what is the scope in theory? Well, it has applications in future directions in like some of the following topics. Okay, so simulation of measurements using other restricted classes of measurements. So this work falls in that category. So the earlier work which I talked about, Mihal's earlier work in 2019, in which like they propose a similar scheme to implement an arbitrary POVM using no ancillary qubits, that also falls into the same category. Now, so this is just work. So this is work basically in this line of like this topic. Then what the significance of Q success? Can Q success be related to other quantities of interest, like for instance the visibility and entanglement cost of measurement, etc. Then it has. Then we believe that there are. Mihal particularly believes that like it may have applications for non-locality, that is randomness generation and local models, etc. And finally, like there's also this thing that you can use the results in this work for simulation of random circuits with other circuits. Yeah, so with this I conclude. Thank you for listening.
Okay, Thank you, Tanmay.
Sure.
May I ask a question? In
Sure.
the very beginning, you assume the rank of M is equal to 1, so does your result restricted to this rank?
Rank one.
So if the rank is different, is higher, your ancillary should be more, right? Or
no. So sorry to interrupt. Like I'll just answer that. So the thing is, like, suppose I have a measurement in which the rank of the outcomes, sorry, the rank of the POV effects, let's say it's greater than 1, then you can always, find another POVM, okay, which has, more number of outcomes, but in which each case the rank of each POVMs is precisely 1, and the former POVM is actually a post-processing of this latter POVM which has only rank 1 outcomes. In other words, you can always decompose, you can always find another POVM which corresponds to the original POVM in which, outcomes are all rank 1. So this still applies to that case.
okay.
Hi. May I ask a question? So, you're saying that basically you can achieve any. I think you conjecture you can achieve any POVM using only 1 qubit and classical resources. And is there, so if you do kind of a full analysis of the actual classical costs, like is there some hidden hardness in the classical computation?
So like, look, in the scheme, the scheme, like, okay, so the probability that you use over here, this is a fixed probability, and this post selection is also actually not all that difficult. So like in that sense, like there is no cost associated with this. But then I will mention one thing. So okay, so consider the case where okay, I think I should just right. Okay, so right. The thing is that, you see, to implement this scheme, what happens is that you actually have to implement all of these POVMs, NX1 and X2, so on and so forth. Okay, so how many POVMs are there? There are K POVMs, right? Now each of these will require their own circuits, right? Suppose N is equal to D square and M is equal to D. Okay, so that is actually the most interesting case. Okay, so because, I mean, you get the highest probability, success probability for those. Then what happens is that K is also equal to D. What that tells you is that the number of circuits that you have to prepare, okay, to implement the original POVM, that is equal to D. So this has that particular downside that, like, as the dimension increases, like, yeah, you can implement it with a single ancillary qubit, yes, but the number of circuits that you need to prepare is, also it increases as a function of the dimension. So that is, I think, one of the downsides of this, or that is like one of the costs associated with this, which has not been, so this is a hardware cost, and this has not been incorporated there is, in this analysis so far.
Thank you.
Oh, yeah. Hello. So
Yeah.
I think I have 2 questions. So maybe the first one, which is about the HAR result. So you mentioned that analytically you could show it's like the success probability is greater than like some number of percent, like 6.5%. Yeah, 6.5 or something. But the numerical results show that it's like 25.
Right.
Is there some work on like improving this analytic bound, or
yeah? So
what would you say about it?
So the thing is that, like, so I put a lot of effort into like trying to get like something like 20. Actually, to be honest, like we believe that this over here, like asymptotically, we believe using results from free probability theory that you actually get 25%. Okay, so but there is a snag in that calculation. So that is why we did not include that result. So asymptotically, we know that on average we will get 25%. Of course, like with free probability theory, you don't have results on the concentration. Okay, it just tells you something about the asymptotics. So regarding concentration, like again, like we tried very hard. Like I particularly tried very hard to get 25% or something higher than 6.5%. But yeah, this is finally what we obtained. So yeah, in that sense, like we were sort of limited in getting that. So initially it used to be 2.7%, and using some tricks here and there, we managed it. We increased to like 6.5, and then we just remained happy with it.
I see. Is there some work on the just the expectation part, like for free probability? So I'm just saying that 25% looks like a really interesting value, like 1/4. So I don't know.
Yeah. So free probability actually so actually the thing is like there is like whatever calculations we did, okay, that gives you 25%. Okay, that again remember that is the average value of Q success over the entire unitary. Okay, it does not tell you the concentration. That gives you 25%, except that there is a snag in that calculation. So, okay. But yeah, we do feel that there is a strong indication that it's 25% ish.
Yeah, because it's such a nice value.
Right.
Yeah. Okay, so some other questions. So, have anyone tried to replace this hard random with something like, say, T design or some weaker randomness?
The thing with replacing it, okay, so wait. So again, in that case, so the original POVMs that you want to simulate are hard random POVMs, or are they like other POVMs? No, that's a question to you.
Okay.
So like, what is the question? What is the POVM that you want to simulate? Are they hard random POVMs, or are they like some other random POVMs, or like are they like random POVMs, but let's say with a discrete probability distribution? So what is it that you would like to simulate?
I guess I don't know.
Okay, sure. Okay, so let me
the next question I'm going to ask is like specialized to stabilizer. Like, is there something that's specialized to stabilizer? But you can comment on later.
I mean, okay, so one thing I can mention is that suppose you want to implement hard random POVMs. Okay, so you can ask the question, fine, great. Can you get like some result, okay, using like like a discrete probability distribution on the unitaries, let's say unitary design? Well, the answer is no, because the thing is that the quantities that you want to optimize over, okay, or find the averages or find the concentration of these quantities, they are not polynomials in U and U star. Okay, so they're sort of a more complicated function. Okay, they're not polynomial functions. So if you want to approximate or you want to find results on those functions of this U, so Q success is a function of U. I'm saying that like Q success is not a polynomial function of U. And because of that, you can't use a unitary design sort of thing to get this kind of result. But I don't know if that was what your question was. Anyway.
I guess my question is kind of vague. Maybe just like, is there some relation, like kind of aversion in the T design world? Yeah, I see.
Okay.
And so the last question is, well, sorry if the question doesn't make sense. Like, does this, like, is there a sense of like you specialize these U to stabilizer types? So in the sense that now U is not the full unitary group, but like stabilizer group or something?
Sure. I mean, yeah, you could do that, but I mean, yeah, you could do that. And I mean, the thing is like, so in that case, like what you would get some sort of result like this. You would get like a result where, you have, let's say, actually, no, you could even perhaps do it analytically. But yeah, we did not it did not occur to us to compute it for like a stabilizer subgroup of this UD square and then obtain the relevant POVMs for those and then obtain like, such kind of concentration for that.
Mm-hmm.
Actually, the thing is like we already have a result, okay, which tells us that like, we actually, this conjecture is already sort of true. We already know that this conjecture is true. We already actually, no, sorry, we have what? We have 1 by log D or something like that. We don't have a constant here yet, but we have like a fairly decent scaling already.
I see.
So the thing is like, even for, okay, yeah, but so for the POVM that you just talked about, like, if you were to replace the unitary with, let's say, a discrete probability of, let's say, stabilized group or whatever, Clifford, whatever, then that would also follow the same law. But I don't know the exact number that you'll get here.
Yeah, thank you.
Sure.
So I have a question, a bit more technical.
Sure.
So in the concentration, there's like a D log D. I think this is not very common in these kind of calculation. And can you comment on what inequality leads to this D log D? Usually it's like minus D or something.
So what is it that we used? Okay, I did this, I did these calculations, I think. So we use log Sobolev inequalities. So in log Sobolev inequalities, the concentration that you get did typically of the form exponential power minus something, right? Or at least for the cases that I've seen for hard random stuff, you get something like this. So yeah, so actually this log D factor, actually, I have a way of removing this log D factor. So it's just exponential minus C times D. I can get that. But I mean, the log D doesn't play that much of a role. So
I see. Okay.
Yeah.
Thank you.
Sure.
Sorry, Tanmay, I would like to ask again the very basic question.
Sure.
I'm just, can you explain again what's the relation of N and D in the general sense? So the N is the system size for the state one, so it's given. So your in general, you have to design D to match how to get the outcome, right? Or do I understand correct?
Okay, so N is the number of outcomes. Little n is the number of outcomes, and D is the dimension of the system. Okay, now you may be slightly. So the thing is, for this talk, what happened is that I use the value little n in two places. Okay, and the thing is they mean different things in two different places. One is the number of qubits. Okay, so this little n over here, that is just restricted to this diagram. I did not mean to sort of say, okay, it's n qubits as well as n number of outcomes. So the number of outcomes is little n and the dimension is D. And this scheme you can use this scheme whenever you can use the scheme for any value of n, but let's say for a non-projective measurement. Does that answer part of your question?
Oh, okay, thanks. So does anyone still have further questions?
Hi, I have a question. So, does your work for continuous POVM?
So you're talking about POVMs in infinite dimension?
No, the number of POVM elements.
The number of POVM elements.
So I'm wondering if your result depend on the cardinality for in this slide, the n, this small n. But what if this n is infinite?
Yeah, I mean, if it is infinite, then so actually from the outset, maybe there is an imitation of the same general principles to something else, which may work for the case where the index is, let's say, continuous. Okay, maybe there is some principle involved there. Okay, but as of now, you see over here, you see you have to choose a partition of the number of. So yeah, maybe there is some way of generalizing to that case, but yeah, that has not occurred to us immediately. Yeah. Okay. But yeah, that is an interesting question that one could ask.
Yeah.
So one would have to take a partitioning in the outcomes, and there has to be some such similar thing over there as well.
Yes. Thanks.
Sure.
Hi, I'm going to ask another one. So
sure.
So you mentioned there might be some very small, extraordinary hard POVM that might not match this 25%, something like that. And can you comment on what kind of POVM are those?
So
what to expect for them? Yeah.
So the thing is that so look, what this result basically tells you that wait, hang on a second, just give me a second. Right, so the thing is that like what happens over here is that we have fixed a partitioning, okay, and for that fixed choice of partitioning you find that this Q success, like for that fixed choice of partitioning you find this kind of behavior for the Q success, okay. So what this tells you is that for this fixed partitioning you will have some Q success, a large number of guys will have Q success greater than 6.5%, and a smaller subset of them will have Q success less than 6.5%. I mean, I know that I'm not answering your question so far. I'll come to it. The point is that if you choose, let's say, another choice of partitioning, okay, then you will have a similar distribution, but this red circle it's likely to be somewhere else, somewhere sitting over here, okay.
Oh.
And then if you were to choose another choice of partitioning, the red circle will be sitting somewhere over here, so on and so forth. Basically tells you the basic thing is that there will be some choice of partitioning, okay, such that when you implement the scheme for that choice of partitioning, you will find 6.5%. So actually this result is pretty strong in the sense that it tells you that like you can be assured to do pretty well regardless of your choice of partitioning.
So it's not that you have some weird POVM that's going to break it, but just that this concentration is just something else. I see.
So basically, yeah. So basically, what you can think is like, look, so you have some POVMs, okay, and then you have made some choice of partitioning. Maybe there is some weirdness going on between the relation of that POVM and this choice of partitioning. And if you were to choose another choice of partitioning, then you would have like the scheme work fine for those set of POVMs. But for another set of POVMs, now you will have some similar problem.
Okay. Thanks.
Sure.
Okay, does anyone has further questions or comment? Okay, if not, thanks Tanmay again. Thanks.
Thank you very much.
Okay, thanks for the nice talk.
Thank you.
Okay, thank you. So, so if anyone was interested in giving a talk in the future, anytime you are very welcome. Okay, thank you, and thank you for Tanmay's talk today. Thanks all.
Thank you for having me. Okay, so